Hey guys, here is our lesson on the applications of exponentials and logs. And I'm in our textbook because I just want to show you a few places that are going to play an important role to you. So the first one is this graph right in here, in this box. And in there you'll notice that they just say what the characteristics of any exponential function is. And so they list it like that. A lot of times, and it's totally fine for you to use this also, they will use y equals p naught e to the rt. That's usually for money and interest, where p naught is the principal and r is the rate. But if you go through here, all of these things are things that we've talked about. It's one-to-one, meaning that there is only one value for every input. There is a horizontal asymptote at 0 because it never touches there. The domain's everything because it does go forever. There is no x-intercept because it never crosses. The y-intercept, whatever that a is out there. And why is that the y-intercept? Because the y-intercept is when x is 0, or in this case, t is 0. And if t was 0 right here, we would have e to the 0. And e to the 0 is 1. And a naught times 1 is just a naught. So when t is 0, this value will always just equal that number right there. And so that's why they are so certain when they say that will be the y-intercept, because that is what the y-intercept is. And then if k is bigger than 0, you're going to get this growth look. And if k is negative, meaning less than 0, it's decay. So it will decay down. There's some cool stuff in here about half-life. I'm going to talk about it in a second. There's stuff about radiocarbon dating. We will probably return to this spot here in the book. Finding the age of something, doubling time, and Newton's law of cooling we will get to. And so we're going to pop in and out of this quite a bit. So I'm going to come over here, and here's the few things that I have written down that we're going to talk about. So the y equals a naught e to the kt, or y equals p naught e to the rt. These are both exponential functions, and a naught or p naught is the initial population or the initial amount. And it's because, what does initial mean? Initial means initially, well, that's when time started. So at that point, time was 0, and that would tell us what we started at. So those are the initial population. And what k is it's a growth rate. And I'm going to say growth or decay rate. And a rate is a percent, but we use it as a decimal. And it's not the actual percent. It's more of the annual percent. So I'll talk about that when it comes there. Half-life, this is going to play an important role. So what half-life means is for substances that radiate or lose population, lose substance, lose whatever, and does it in an exponential manner, there is some time for which there will be half of whatever you started left. And that always weirded me out as a student, because if I started, let's say that something had a half-life of 100 years. So there's some substance that has a half-life of 100 years. And if I started here with 1 gram of that thing, and you started at your house and you had 1 pound of it, and we both waited exactly 100 years. After 100 years, I would have a half gram left. But after 100 years, you'd still have 8 full ounces left, or a half pound. And what kind of boggles my mind is it's the same time. And so how do the substances know, oh, but we only started with a smaller amount, so we can't lose, we can only afford to lose about a half gram. But over here, we weren't worried about just losing a half gram here. Here we lost 8 ounces, and that's quite a bit more than just a gram or a half gram. So anyway, that's the story behind half-life, and there is some cool formulas for it, and so I'm going to tell you a little bit more about this, and you'll hear this. You may want to rewind and watch this over again once we do a few problems, and then you can see where I talked in the beginning about how all of this was going to come to play. Right now I'm just laying it out so that I've said it, so that when we move to the problems and we need it, I can come back here and say, do you remember when we did that? And then you'll be more comfortable with it. So let's go through what half-life looks like. So if A naught e to the kt is the initial amount, that's the amount that we have for any time, what I want to know, and why is that amount? So in this book, when they have that, they should say it somewhere, but why is the amount of the substance that there is? And A naught is the initial amount, and K is some percent of the population that's either growing or decaying. And so if I want the half-life, I want to know, when is there half the initial amount? Remember, that number is the initial amount, because when t is 0, that disappears because it's 1. And so at 0, we always have A naught. So I know that's my starting amount. So if I want to know when will there be half of it left, then I'm trying to find when we get half that amount. And the really, really cool thing about this, you guys, is that when you divide both sides by A0, this is where the gram and the pound starts to make sense. It turns out, because those cancel, it doesn't matter how much you started with. And so it really, this shows that the losing a half gram or a half pound in the same amount of time, it didn't matter how much you started with, it's going to lose it at a rate. And so if there's more there, more of that bigger percentage is going to fall off over time. So anyway, we get then 1/2 equals e to the kt. And here's where all of the previous sections, like the solving equations, doing all that stuff, this is where it comes together. Because I want to solve for t, because half-life is a time. So I want to solve this for this variable t here. Well, t's in the power, and so how do I get it out of the power? I ln both sides. So I got ln of a half equals ln of e to the kt. Now, ln of e to the x has equaled x for us. That's that ln, and those, how they cancel each other out. So those cancel each other out. And we get ln of 1/2 equals kt. And if you divide by k, you get t equals ln of 1/2 over k. And so this is the formula right here for half-life. And in our textbook here, when they talk about half-life right here, you can see they set it up the same. They do all of the same types of things. And then they move to this. I don't like this at all, and I don't like this at all. And I'm going to tell you why. But here's all they did. They just said that ln of 1/2 is really ln of 2 to the negative 1 power. And then they said, oh, let's bring that power down, and it's negative ln 2. And so that's how they got that value right there. Don't worry about that. But notice, and I'll tell you why right now, actually, because we may as well do this. So I'm going to just erase this part, and we're going to move on to the next piece. And that next piece is doubling time. So equally likely with half-life. So half-life only works with decaying things. If you're growing, there's never going to be a time when there's only half of what you started with, because you just told me it was always growing. And so how would there be half left? But if it's always growing, there will come a time when you have twice what you started with. And so that's what doubling time is. So these are both times, And they're both very specific times in the evolution of this process, whatever it is. So with doubling time, it's the same thing. I know a naught e to the kt is how much there is at any time. We can put that in here. Y equals the amount at time t. So it's really y of t. You know that because there's the variable right there, but we don't usually write it. So if I want doubling time, and that is the initial amount, then I want to know when will there be twice that amount there. Similarly as before, when you divide by a 0 on both sides, that amount doesn't matter. So then you get 2 is e to the kt. ln both sides, you get ln of 2 is kt. And then divide, you get t is the ln of 2 over k. So that's the doubling time. And here's why I like these formulas better than the book's formulas. So the book has a negative ln2 for half-life right here. We're in the half-life section. If we move a couple pages here, we have doubling time. And see, they have the ln2 over k. We have ln2 over k. But we disagree here. And we don't disagree. They just took it a little farther. We agree right there. But here's why I like it. Half-life is ln of a half. Double time is ln of 2. They're both over k. So half, you put a half in there. Double means 2 times, and so put a 2 in there. That's why I like it. And then the final thing in here, and I'll show it to you more than just writing it down. I'll show it to you in the book. Newton's law of cooling. So here is Newton's law of cooling. And what it says is that the temperature of an object T, so this is temperature, capital T is temperature, and little t is time. And so they tell you right there that's time. Then the temperature of an object at any time is equal to ae to the kt plus ts. And they tell you somewhere ts is the surrounding air temperature. I was looking for the word surrounding. So S is for surrounding. So they'll usually say like the ambient temperature or some, oh yeah, they have that word right down here. But they will say like the ambient temperature in the room is held at a constant 70 degrees. That's TS is 70. So, and then a lot of books, instead of an A right there, they use a D naught. And D naught could be used right there. What that is, and I'm going to show you this when we do the problem, it's the initial temp difference. And I'm going to tell you that now, and I'm going to leave it and I'll show it to you later. Okay? So, that is, in a nutshell, I know that's fast. So, but you got the book to read, and you have other things that you can look at. So this is an exponential growth or decay function. The a naught is always the initial amount. The k is always some constant that determines growth or decay. In there, if it's decaying, you might be concerned with the half-life, and if it's growing, you might be concerned with the doubling time. And if it's not something that's radioactive or like interest growing or bearing or something like that, then it could be something heated up and be cooling off. And so there's what we got. Let's take it to these problems. So I want to show you how the problems are kind of hard, but they're only hard if you overthink them. So this says a subject has a half-life of 2.045 minutes. Okay. So if the initial amount was 132.8, so right when I see that, I'm going to say, okay, well, a naught then is 132.8. And now it's, oh wait, this is weird. It says how many half-lives have passed before the subject decays to 8.3 grams. And so if we were going to do that, all you would have to do is this, do 132.8. Okay, the first half-life, there would be 66 left. So one half-life is 66.4. Divide that now by 2. So 2 half-lives is 33.2. Divide it by 2 again. Now we're at 3 half-lives. In 3 half-lives, we're at 16.6 grams. Divide that by 4, or times 4. Divide it by 2, and we're at 8.3. So I put the 4 because I was on the 4th half-life. If we divide by 2 again, we get 8.3. That's what they said. So how many half-lives will have passed before it goes? 4 of them will have passed. And then it says, what is that total time? What's the total time it takes to decay? Well, here's the deal. If you know it's 4 half-lives, and you know each half-life is 2.045 minutes, then if you took 2.045 and multiplied it by 4, you would get that the answer to this part is 8.18 minutes. And this is 4 half-lives. So it takes 4 half-lives for it to go from 132 grams to 8 grams, basically. And in those 4 half-lives, each one lasts 2.045 minutes. And so it literally takes 8 minutes to radiate off almost that entire sample. Like you started with 132 grams, and after 8 minutes, you have under 10 grams left. That's crazy. Now, that's kind of the easy way of thinking this problem, okay? But there's another way of doing it, and this is the way that I initially did it in the beginning. And so, remember our answer was 8.18. And here's how it's more complicated, but in doing this, you start to understand it better, and you start to learn things as you go. So remember, the half-life formula was T equals ln of 1/2 over K. And I know my function is y equals a naught e to the kt. And so I know my a naught. I know it's 132.8 e to the kt, and I just need to figure out k. That's all I need to know. Well, if I multiply by k up here, multiply both sides, it'll cancel. Then you got kt is ln of 1/2. So k is the ln of 1/2 divided by t. And t is not any old time. T is the actual known half-life of that object. And so if I took k to be ln of 1/2 over, and the time is 2.045 minutes, then I've got k. So let's go 2.045. Let's go ln of 0.5 divided by 2.045. That gives me a k of negative 0.3389472766. So I know now my formula is 132.8 e to the negative 0.33894726766 times t. And now I can say, well, I want to know when will it come out to be 8.3 grams. So I need to know how long until that becomes my y value. And what I'm going to do then is say 8.3 equals 132.8 e to, and I'm going to abbreviate now, I'm going to say 0.33 ... t. Now I want to solve for t, because that will be the time. Remember, we have the answer up here, and we got it a lot easier way. But you won't always have this, so you do need to know this other process that I'm doing. First thing I'm going to do is divide both sides by 132.8. So I'm going to divide by 132.8. Those cancel, and I get 8.3 divided by 132.8 equals e to the negative 0.33 ... t. Now I'm going to ln both sides, and I'm going to cheat a little bit, so I'm going to just put it here, but that's because I've told you. And when I do that, those cancel. That was the motivation for doing it. So I now have the ln of 8.3 over 132.8 equals this negative 0.33 dot 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 t. So all I have to do is divide by the negative 0.33 dot dot dot, and that's gone, and it will be the answer for t. So there I've solved for t. And watch this now. If I do the ln of 8.3 divided by 132.8, and that whole thing's divided by negative 0.3389472766. It's pretty close. If I used here the ln of 0.5 divided by 2.045 and kept it, whoops, it didn't come out, and you can see this. I forget to push the over arrow to get out of the ln. That 2.045 really has to be on the bottom. So now it's my previous answer. And what I could do is actually say ln of 8.3 divided by 132.8 divided by, and set it to that answer. And then it is 8.18, which is exactly that time that we got there. Now that I know that the total time is 8.18 minutes, if I took 8.18 and divided that by the 2.045 minutes that each one was, it comes out to be exactly 4 half-lives. Notice that's what we got the first time. But the first time, I just sort of, it felt like I was almost cheating because I just started and said, okay, divide by 2, divide by 2, divide by 2, divide by, oh, there it is, divide by 2, it's 4. And then they said, well, how much time is 4 half-lives? Well, it's just 4 times that 2.045. And that came to be that number. But if I took the 8.18 and divided by 2.045, it tells me it's 4 half-lives. I know that second way was harder, but it really is a better way of thinking about it. And so let's take a look at a problem like this. I'm going to do 29, even though it's one of yours, just because I want to show you something, and then you can check the answer in the back of the book, because there's a little weird caveat in this, and you really got to pay attention to what I'm saying right now. So when we read the statement of this problem, it says, use this scenario for the following problems. A doctor is going to give 125 milligrams of some drug, and it decays by about 30% an hour. So a lot of people, if you take it just literally, they will take K to be negative 0.3. That's what it would be if it dropped that much. But if you really want to know what it is, what does it mean if it decays 30% each hour? That means that after 1 hour, 70% will remain. And so what I want to do then is, when I set this up this time, I'm going to say 0.7 A naught equals A naught e to the k times 1. Why is it k times 1? Because it's each hour. So I know this happens at that spot in time. And so then again, dividing off the A naughts, they go away. I get 0.7 equals e to the k. If I ln both sides, I get the ln of 0.7 is is the ln of e to the k. The ln and the e cancel, and I get k is the ln of 0.7. And so if I take the ln of 0.7, it's negative, but it's 0.356674949, and that's close to negative 30%, but it's actually negative 35%, 35.667494333. And because that happens, it's not exactly that value. And in the back of the book, I think if we go 877, here in problem 29, right here, they have that negative 0.3567, and that, whoops, is what we have right there. So that's how they get it in the back of the book. It's not that you take that, but you take that and ask, what does that mean for you? If it drops by about 30% each hour, that means after 1 hour, 70% remains. And that's a little bit different than it dropping by 30%. So then now I know the function. It's 125, because that's my initial value. That's the A naught. So in that, I knew right away A naught was 125. And then we have e to the k, and that's negative 0.3567 t. And then they say how much after 3 hours. And so in this, since I have that there, I could say 125 times e to the, I'm going to say answer, times 3. And the reason is because this is my k, and there's my k right there, but my k is the last line in there. So it's like 42.875 is what it comes out, 42.875. And if you check the book, it says about 43. So about 43 is, yeah, that's about 43. So, oh, and they say round to the nearest milligram. So, yeah, to the nearest it would be about 43. So that's how you do a problem like that. Then, let's see, that's the same one. Okay, so in this problem, now, notice it says a wooden artifact contains 60% of the carbon-14. So I want you guys to read this kind of on your own, just because I don't want to take a bunch of time making you watch me read it to you. But in this book, if we go back to 553, in here, when you read about right here, radiocarbon dating, it's very interesting how it came to be, and how we figured out that there is some ratio of carbon-14 to carbon-12 in the atmosphere. And the fact that we can determine that ratio, then we know if you're alive, you exchange this carbon to and from the atmosphere, and when you die, you stop trading out your carbon, and so then whatever carbon you had at time of death starts to decay because you're no longer replenishing it or trading it out, and so for that reason, it works, and it's extremely useful. And the carbon-14, since everything that's biological, at least on Earth, is carbon-based, and it's carbon-14 based, and we know the half-life of carbon-14 is 5,730 years. So that is useful, and this is something that you have to know this. A lot of times they tell it to you, but this number never changes. Anytime they say carbon-14, it's 5,730 years. As a matter of fact, if I just even went here and said, what is the half-life of carbon-14? Let's see, you can do it. Approximately 5,700 years, but it'll tell you exactly 5,730 years plus or minus 40 years. That's the half-life of carbon-14. So since we know that, that's pretty useful. And so here's what we got. So I can now figure out the K because, and on the other page, I think, yeah, we moved it around. So if I move the T up there and the K down there, we can switch it around. So in this, There's the ln of a half, because we're talking about half-life. And I know the time, the t in there, so this will give me the k. And if I do that, then let's see, so we have ln of 0.5, not negative 0.5, but 0.5 divided by 5730 is negative 0.0001209,681. And that's also standard in the book. You see they have that negative 0.000121. That is exactly that number if you round the 9 and round that 0 up 1. So that's where that number comes from in there. But that gives us k. So I now know k is approximately negative 0.000121. Okay, then I know this, that I only have 60% of the original amount. And so that means that 0.6 of the original amount should equal the original amount, e to the k. I now know k, t. And I can now solve for t. Dividing off the a naughts, they don't matter. That's the cool thing. So now I've got 0.6 equals negative 0.000121t, or e to the, sorry. ln both sides, I'm going to cheat and say ln here and ln here. The ln and the e wipe, that's why I didn't write it in the last step. 0.6 is negative 0.000121t. And if I divide by that number, I've solved for t. So negative 0.000121. What I like to do, and notice this, so the book will just use that value, but the actual value is 0.001209681. And those decimals, you're like, oh, they're out in the 10 thousandths and 100 thousandths and millionths. And yeah, but on massive years time scale, it's noticeable, and it matters. And so if I take the ln of 0.6, instead of dividing and typing it in, I'm going to say, let's divide that by the previous answer. So now I'm using all of the decimals, and I get that it is 4,222 years old. So I would say it's about 4,222 years old. But I figured out how, and you guys, this is how they do dinosaur bones and things like that. They'll dig them up, and they'll make an estimation on how much percent of carbon is left in the sample of bone. They know how much should be there. They can test through chemistry how much is actually there. So then they know the percent that's there and the percent they expected. And based on how much is actually there, they can extrapolate out over the half-life and figure out how old an object is on Earth. That's pretty cool. I'm going to stop there. I have 2 more problems for us to do, and I'm going to make that in a second video. It's because these 2 problems are my favorite problems, and I'm going to kind of front load you right now for what they are. Notice this one says you have 360 bacteria after 5 minutes and 1,000 bacteria after 20 minutes. So you don't know how much you started with. You only know that after 5 minutes there was 360, and after 20 minutes there was 1,000. But you don't know how much to start with. And so we need to do something different in this problem. And the final problem used Newton's law of cooling. And when we hit Newton's law of cooling, I'm going to come back here and remind us of that right there. So I'll make the next video, upload it later, and get it to you guys as soon as possible. All right? Hang in there. Take care. I'm proud of you. Bye-bye.